So we've seen that every vector subspace has an orthogonal complement. Let's use that observation to prove this important result, the orthogonal decomposition theorem. So let's let W be a subspace of Rn, and let's let X be some vector in Rn. Okay, not necessarily in W. Okay, just somewhere in Rn. Then what we could do is we can decompose vector X into a vector in subspace W and a vector orthogonal to subspace W, something that is in the orthogonal complement. Okay? What's more, not only does this decomposition exist, it is unique, which means there is exactly one pair of vectors in W and W perp. Okay? There's one W in W and one vector W in subspace W, and one vector W perp in subspace W perp, so that this decomposition will work. Okay, let me show you graphically what we're saying here. So let this be a subspace W. Okay, and say we have some vector X in Rn. Okay, what we could do is we can decompose X so that there'll be one vector in subspace W and then another vector orthogonal to subspace W, so that when I add them together, I get vector X. Okay? So let's go ahead and prove this. Now, because we want to prove there exists a unique vectors, that's actually a two-part proof. We first need to prove existence, and then show that that is unique, that it's the only way to do it. Okay? So let's start by letting X be some vector in Rn. We don't care which one. And let's let the set of vectors f1, f2, all the way to fm. Let's let this set be an orthogonal basis. For subspace W. Okay? We've seen in the past that as long as we have a basis, we can use the Gram-Schmidt process to turn it into an orthogonal basis. So vector space W, subspace W, will have an orthogonal basis. Okay? Now, what we need is a candidate for vector W and vector W perp. All right? Let's set vector W equal to the projection of X onto subspace W. All right? And W perp, we're going to use a little bit of a trick here. Since I know I want X to be equal to vector W plus W perp, that also means that W perp better be equal to vector X minus vector W. So if W perp is going to be the projection of X onto subspace W, then I can easily find W perp by just subtracting vector W from vector X. So W perp is going to be vector X minus vector W. Okay, now what we need to show, now clearly, if I take these two vectors and add them together, I'm going to get vector X, right? if I plug in x equals vector w, and then I add to that w perp, which is x minus w, vectors w cancel out, and I get just x. Okay, so that part of the proof is pretty obvious. I'm not even going to mention it. All right, clearly the sum is true. What we need to show, though, is that w perp is actually in the orthogonal complement of w. Okay, that is that that vector w perp is going to be orthogonal to every vector in subspace W. So first, let's kind of expand W perp out. That's going to be x minus vector W, which is x minus vector W we've defined as the projection of x onto subspace W. Now we've seen how to actually calculate that. With an orthogonal basis, you are going to just project x onto each vector in the orthogonal basis. So f1 dot x over norm of f1 squared times f1 plus, do the same thing with f2, and so on. Now what we want to do is we want to show that this vector is orthogonal to every vector in W, in subspace W, and therefore this vector actually really is in the orthogonal complement of W. It is in subspace W perp. Now to do that, instead of looking at every single possible vector in W, remember this is a basis for subspace W, and therefore this is a spanning set for subspace W, right? And so if W perp is orthogonal to every vector in the spanning set, it's also orthogonal to every vector in W. So what I'm going to do is I'm just going to take the dot product of one of these vectors in my basis for subspace W with W perp and show that that is 0. Observe. So here I have f1, f2, fm. I really don't care which one I pick. I need to show it's true for all of them, so I'm going to choose fi. I could be 1 or 2 or 3 all the way to m. Okay, I'm going to take the dot product of that with w perp. Okay, so that means I'm going to take the dot product of it with all of this. So I get fi dot x, okay, and then I'm just going to distribute it through. So dot product of fi with this first guy, and then with this guy, and then with this guy, and then with this guy. So f1 dot x over norm of f1 squared times fi dot f1 plus, and I go all the way into the last one, fm dot x over norm of fm squared. This is just the coefficient. And then I take the dot product with the vector. So fi dot fm. Okay? But this isn't just any old basis. This is an orthogonal basis, which means all the vectors are orthogonal to each other. So fi, the dot product of fi and 1 and fi and m, and all of these are 0 except when I is equal to whichever the other one I'm taking the dot product of. If I is different than this subscript, then the dot product is 0 because they're orthogonal. The only case when it's not 0 is when the subscript here and the subscript here are equal. So I get fi dot x minus, and then the only one that's going to be left here is fi. And that's going to be true for any subscript I. All the other ones are going to vanish because they're just equal to 0, since the dot product will be orthogonal, since we're dealing with an orthogonal basis. Okay? But notice what happens. Norm of fi squared is just the dot product of a vector with itself. Okay, remember, this is the norm of fi squared. Just another way to write it. They're equal. And so this and this will cancel, leaving me the dot product of fi with x minus the dot product of fi with x. And of course, that is equal to 0. Okay? Now that's true for each of these. Remember, I used f sub I, which means I could be 1 or 2 or m. The argument works for all of them. So therefore, w perp is orthogonal to every vector in the basis. So w perp is orthogonal to every vector in my basis, f1 all the way to fm, right? Because we just showed that the dot product of them is 0. And that's the definition of being orthogonal. Okay? And since it's an orthogonal to every vector in the basis, and this basis spans W, it's also orthogonal to W. Meaning W perp is orthogonal to every vector in subspace W. And being orthogonal to every vector in subspace W is exactly what it means to be in the orthogonal complement of a subspace. Okay, so therefore vector W perp is in subspace W perp, the orthogonal complement of subspace W. Okay, so that's the first part done. Okay, we've shown existence. We've said, hey, if you set vector W equal to the projection of x onto the subspace, and you set W perp equal to x minus vector W, then x is equal to the sum of these. Obviously, that's clear. I don't even have to throw it in the proof. It's obvious enough. Okay, but also we showed that, first off, W by definition, vector W is in subspace W. The tricky part was showing that W perp was in the orthogonal complement of W, and that's what all of this was about. Okay, so we've shown existence. We still need to show uniqueness. We need to show this is the only way that we can do this. So now let's show uniqueness. All right. Suppose, let's call it U and W. Two vectors U and W are in W, or in subspace W. And two vectors U perp and W perp are in the orthogonal complement to subspace W, such that x is equal to vector W plus vector W perp, but also equal to vector U plus vector U perp. Okay? This is a standard way we show uniqueness. We say, hey, what if there are two? And then what we need to do is show that they're really the same thing after all. Okay? So what I'm going to do is I'm going to take this, and I'm going to manipulate it algebraically. Then W plus W perp equals U plus U perp, right? Which implies what I'm going to do is subtract the U, and these should be vectors, throw the arrow above them. Subtract the U to the left, subtract W perp to the right. That way, both of these vectors are in subspace W, and both of these vectors are in the orthogonal complements W. Okay? Then for any V in the original subspace W, if what I'm going to do is I'm going to take the dot product of V on both sides. Okay? Now what's going on this right side? U perp, W perp, they're in the orthogonal complement of W, which is a subspace, right? Which means it's closed under addition, it's closed under scalar multiplication. So when I subtract these, this new vector is also in the orthogonal complement. Now, since V is in W, the dot product, every vector in W is orthogonal to every vector in W perp. Okay, so V is going to be orthogonal to this, which means the dot product of these is going to be 0. Okay? Right? Now, this is true for any vector V in W. Okay? Which means any vector V, take the dot product with this, we get 0. What that means, that by definition, that means this is going to be orthogonal to every vector in W. And so this vector, this difference, has to be in W perp. So W minus U is in W perp. Okay? But W is a subspace. So it's closed under addition, it's closed under scalar multiplication. So W minus U is also in W. The only vector that's in both W and W perp is the 0 vector. That's the only vector that could be in both because it's the only vector that's orthogonal to itself. Okay? Every vector in here has to be orthogonal to this. Every vector in W has to be orthogonal to every vector in W perp. The only way you could be in both is if you take the dot product with yourself and you get 0. And the only way you could do that is if it's the 0 vector. All right? Which means, since this vector, W minus U, is in both W and W perp, W minus U has to be the 0 vector, meaning that vector W has to be equal to vector U. They're really the same vector. Okay, so I started with 2 and then showed, well, wait a second, if I satisfy this condition, they're really the same thing. Okay? A similar argument, and I won't go through the exact details because it's the exact same argument, just flipped around. But a similar argument shows vector W perp is equal to vector U perp. Okay? And that this proves uniqueness. Okay? And just to emphasize, we started this argument with two different vectors, a u and a w, a u perp and a w perp. Two ways to decompose vector x. Okay? But then we showed, well, wait a second. Actually, when we look into it, those two, the vectors have to be equal. The decomposition has to be the same. And so the decomposition is unique. There's only one way to do it.